let us see. The summary of this model is very simple. Remember, the model is A new. Hello, welcome once again. This is Samuel Ambrose Onen. I'm just giving you the summary of the model and to just show you how this model can be used, which is very natural for me. So let us see. The summary of this model is very simple. Remember, the model is A new equal to B, where A is our computational problem and new is the solution to that problem. Because if any problem exists, there must be a solution to it. But we don't know that solution. But we expect to get something from the problems and the solution. Because the solution begins at the point where we know the problem. You cannot solve problem without knowing where to begin from. You cannot have the solution to the problem without knowing the problem. Otherwise, what are you going to solve? So that is the reason why we came up with this to be like our input into the system. And once we input this in the system, we need to figure out, we need to do some work on A in order to transform A, to become something which will now leave our new as the solution. That's why we say new equal to be a transform, because once we transform A plus the expected output that we want to get, we get the absolute solution to the problem. So in the previous video, I tried to give you some demonstration to show how true is this, how true in this. So we assume that A is some problem which exists somewhere in the space. Just think of the space like what you're seeing in front of you. This is the space. This is the space. What I'm saying in the space. I'm existing in the space. This thing is existing in the space. So the overall space without anything is the whole space. And the instances where things exist on the space, those are the subspaces. So we have some problem in a subspace, and the solution of the problem could be somewhere in um, in another subspace. So what we want to get is now the expected output. What we want to get is the solution to the problem by transforming this A from this space, so that we go from problem space to the solution space. And that is our target in this video. Now, we model A to be like some form of vectors, let's say U, V, W, vectors, some vectors in the space. The reason why we model the problem to be vectors, because problems change with time. They can increase, they can scale up, they can become small, they can be sorted out. So it's like the vectors. So this will be like presented by some kind of R. For example, that could be U, and that could be V, and the other one could be W. But they exist somewhere in the whole space. So we need to find the solution. The solution exists in form of scalar quantity in, for example, Z, Y, X direction, if you like. So that is the solution, because we want to cover the three-dimensional space. So our problem is U, V, W, and the solution to this problem is X, Y, Z. Yeah, this is a solution. But we got the expected output. We want to get something from this problem, and that expected output can be B, which could be another vector as well, which is B1, B2, B3. They're all vectors in the space. Now, how are we going to solve this one? Now, let us give them some quantity, some values, after knowing the existence of the problem in a space. We want to come up with something to symbolize the problem. Let's say the problem in the direction of U is A. A00. A00. I'm not going to use comma here because I'm now quantifying them. And then the problem existing in the direction of V is 0, let's say A1, A2, 0. And the problem existing in the direction of Z is 0, 0, A3. You see? And then the solution, the suggested, the absolute solution that we want to find is XYZ. And the expected output, which is B, is B1, B2, B3. Remember, we have set this one in the form of this equation: A new equals B, where new is that one, A is that one, and our B is that one. So now we want to to work out this problem and find out exactly, does it exist for real? If it does, then how can we now solve it? If the solution exists, then we must find our B1, B2, and B3. And then when we plug that one, because the solution is X, Y, and Z, when we plug the solution here, and then get the product of this one, it must give us B1, B2, and B3. And in that case, this equation must be balanced at the end for us to be satisfied that we have got the solution to our problem. So let us see how to go about it. Let's now use metrics, because this is now a matrix. Now let us multiply them and get the linear combination of these. Remember, this model is based on linear algebra. So we need to find out the linear combination of all these in order to be able to manipulate them and try to work out the solutions. So when you multiply this one, you get A1x plus 0 equals B1. And then you multiply this one, you start from there, then you get 0 plus A2y plus 0 equals to B2. And then we multiply that one again, matrix multiplication. 0 plus 0 plus A3z equals B3. So remember, these are different equations, 1, 2, 3. So solving them from 1, we get x equal to B1 divided by A1. And then the second one, we get y equals to B2 over A2. And then the third one, obviously, is this one. We get z equals to B3 over A3. Now, when we plug x, y, and z there, we must get that one exactly. So let's see when it's going to be the case. Okay, A1, 0, 0, 0, A2, 0, 0, 0, A3. Yeah. We must plug the value of xy, which is b1 over a1, b2 over a2, b3 over a3. Here, is it going to give us b1, b2, b3? Is that going to give us that? Of course, it will. It will. It will. Let's see. Let's see. Let's see how it's going to give us. Now, we can actually do it from here. When you multiply this one, straight away you get b1. Multiply this one with that, straight away you get b2. Multiply this one by that, straight away you get b3. Yeah. So now, is this one the same as b1, b2, b3? The answer is true. This is the solution. We have got the solution to our computational problem. So, my friend, this is how to think in the computer terms, how to think, how to design algorithm to solve computational problem. And I hope this video has been informative, and I would like to thank you for viewing. I will see you in the next video, where we will be exploring yet again the same model to see how we can virtualize this thing, how we can really try to imagine the problems are happening in real life. So thank you for viewing. I would like you to just go to the next video and continue with your learning. I hope you will get there. So thank you for viewing, and I'll see you in the next video. Hello, welcome back once again. This is me. Uh, I'm still demonstrating how this model works. In the previous video, we saw how this model can be applied to solve the problem. And we agreed that um, problem computational problem can be complex or it can be simple. So we came up with the instantiation of the problem in such a way that we have A new equals to B, where B is the expected output. For example, this expected output could be like what a stakeholder, what a business owner is expecting from a given problem that they want to solve. So let's say um, um, I can give you a good example of a simple example. I wanted to talk about big high-tech companies, what they're doing now to get all the datas. But let me use this simple analogy by using factorial. Factorial. Let's say we want to get 5 factorial. We know that we want to get 5 factorial. And we know that if we want to get 5f factorial, there must be a reason for getting it. Maybe we want to get 5 factorial so that we can go out and challenge somebody like, you know what, we know how to do 5 factorial. And if you want me to show you, you need to pay. Give me some money. So factorial is actually is all the numbers, all the product of the number, the product of 5 below 5. Does it make sense? The product of 5 and any number below 5. That is what factorial is all about. Which means if we want to get 5 factorial, we have to get the product of 5 and any numbers below 5, which will be like 5 times 4 times 3 times 2 times 1. So when you multiply 5 times 4, you get 20 times 3, 60 times 2, 120 times 1, 120. So 5 factorial is equal to 120. Now, this is what we want to do. This is how to do it. And this how to do it, my friend, is what this new is all about. And what to do is the problem like solving 5 factorial. So a stakeholder can come with a statement that I want to I want a system to solve 5 factorial. That is a big statement. It's a general statement. Now, you as a programmer or as a software engineer, you have now to break it down to come out with the problem requirements. Yeah, it's called requirements of the system, and then come with a way of solving it. A way of solving it. Way of solving it, which is algorithm. Algorithm, my friend, is a way of solving it. And once you got that algorithm, that will provide the solution to the problem. And once you got the solution to the problem, the value of new times the value of A times new, must be equal to the expected output. And this is where we prove the theory from, prove the model from the other video. So in this case, we are going to try to see how complex can the problem be, because In the previous video, we said, okay, let us instantiate the problem as being A1000, A1000, A1, X, Y, Z. These are the solutions, and then expected output B1, B2, B3. Yes, this is a very simple problem. It's a very simple problem because we have instances in all the dimensions, but the problem is not widespread. Why? Because we only have the dimension of the problem without other factors surrounding the problem. Remember, this is A2, A3. Remember, the dimension of the problem increases the complexity of the problem. What I mean by that is, for example, if you just take A, if you take A, that is a 1D problem. The problem is found in one dimensional space. It could be like at a point or on a straight line. But when you escalate the problem now to uh, 2D, for example, now you are getting increasing the size of the problem in a two-dimensional space. That the complexity of the problem in 2D is greater than the complexity of the problem in 1A. Why? Because you need more steps to write algorithm here to solve this problem than the steps you need to solve the problem in the first dimension. The same thing happens when you select another problem in the third dimensional space. So the level of complexity increases with the increase in the dimension of the problem. Now from here you need many steps. Let's say from here maybe you need two steps, write a function and you solve the problem. Here maybe double, 4 steps. Here maybe triple or double, 6 steps. And it goes on like that up to n dimension. And that, my friend, is how the complexity in algorithm increases with time and space. Now, what about other factors? If you want more tools, you want other things to help you solve the problem, or if the problem is widespread in 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 the 3 dimension, what do you do? For example, you may have a situation where the problem, instead of having just A, let's say we have something like 102, yeah, 102, we have 100, we have 1, let's say 111. You see, now this problem is huge. The problem is found in the first dimension, the problem is found in the third dimension, and some of them are there in the second dimension, but is widespread everywhere. Solving this kind of problem, my friend, will take more time and space as well as the resources of the system. We can see B1, B2, B3. So we are going to solve this problem in the next video, just to show you the number of steps required to solve this problem and number of steps required to solve just the initial problem in each dimension. But we have done the first one already. I'm just going to show you this one just to give you an idea of how complex an algorithm can be. For example, if we add, instead of 0 here, if we add another number, and here we replace 0 with some other number, we would require even more steps. But to keep it simple, I'm just going to use this one just to show you. Maybe we can derive the equation from here and continue in the next video, right? Okay, let me leave it for the next video. Thank you for viewing. I hope this video has been informative. Thank you. Hello, welcome back once again. This is the continuation of the previous video. Remember, we talked about complexity optimization based on the level of dimension without giving example of how we are going to solve problems in each dimension. Here is example. For example, in a lower dimension like at a point or first dimension, we may need things like simple functions and primitive data types just to write a small function to crash those kind of problems. But as the problem becomes big, we may need things to do with data structures like list, maps, stacks, queue, and 1D array, 2D array, 3D array, up to n array to dynamically solve the problem as they increase. That is how we solve problem, and that's why complexity optimization is very important in algorithm design and implementation.